Delighted to be here today, and today we're going to be telling you about some of the analysis we've been doing over the past few years. And for this presentation, it's going to be a tag team with myself and Zach Chu, and we're going to talk about the mitigation options for BC's forest sector. And I will start by introducing the biophysical mitigation potential, the results of our modeling analysis, and then I'll pass it over to Zach, who will handle the economic and socio-economic impacts of implementing those options. I'm a soft speaker, sorry. Yes, I'll hold it a little bit higher. So to start, I just want to emphasize that we are using a systems approach for estimating the mitigation of the forest sector. And this isn't always done. Sometimes it's done in certain parts. They consider it mitigation in the forest or mitigation for harvested wood products. But really, these sectors interact. So from the forest ecosystem, we can have harvest, which creates products to meet society's demands, such as bioenergy and wood products. And these then therefore can substitute for fossil-based energy sources or fossil-based products like steel and concrete. So we include the entire systems approach so we can calculate the mitigation potential. And we do this relative to a baseline, so a business as usual activity. And we want to include mitigation activities that are incremental, that are based on a change in behavior or technology. So how many mitigation options do we look at? Well, many. There are many different interests for the forests, and so we want to look at different options and use the same modeling frameworks to compare them and contrast them. So I'll just walk through all the mitigation options that we looked at. I'll remind you that we had a baseline, which is looking at the forest ecosystem with projections of harvest and slash burning, and also some simplified estimates of wildfire into the future. And so we took a business as usual, and then the incremental activities added on. The first one looked at higher utilization of harvest. So right now you can capture a certain amount of the stem wood for harvest and take that wood out of the forest and transfer it to products. And we said, well, what if we increase that capture percentage? And that means leaving less waste in the cut block, so there's less harvest waste. And we use that wood for products. And we also decided to increase the salvage harvest percentage. So you can harvest live trees and you can harvest dead trees, and you can make wood products out of both. And so we slightly increased the amount of salvage harvest that was going on. And both of these activities mean there's less harvest of live trees, so there's more forest area left behind to continue growing. The second option that we looked at also dealt with harvest residues. And there we decided to capture the harvest residues and use them for bioenergy. So we would take the residues off-site, grind them, and create heat or electricity with stationary combustion. And as a result of there being less forest residues, it requires less abatement of fire risk, so less slash burning emissions. Then the third strategy was to combine these two activities. So they both deal with residue management. So one you can turn into products, one you can turn into bioenergy, or you can do a little bit of both. And so we added those two together. Then the fourth one looked at harvesting less. So we just reduced harvest levels 2% across the board. And then we added a restricted harvest scenario where we did not allow the model to harvest stands that were older than 250 years old. Now these are all forest management options. We can also look at a wood use option. So it doesn't change the amount of harvest, it just shifts the commodities. And so we looked at increasing the amount of longer lived wood products. And by that we took a small shift, 4%, and we said we're not going to make pulp and paper, which we model as a 2.5-year half-life. We're going to make panels, and that has a 25-year half-life. And when we make panels, we can substitute for fossil products like steel and concrete and put it into buildings. So I'm going to just jump into the mitigation results. I do want to tell you that at this stage we're looking for feedback. We're providing information on the assumptions and the results, and we're looking for feedback. We know there's things that can be tweaked and changed, and we want to work on those. And we're looking for input. So please give us anything you're really looking for. Now on the left, typically what you see presented is, for greenhouse gas mitigation, is an annual emissions reduction, and there'll be a baseline, and then there'll be a mitigation scenario. Now the forest can be a source or a sink, depending on what the disturbances are. So these tend to be quite noisy. So what we do is we subtract the mitigation scenario from the baseline, And we tend to show it as a cumulative mitigation on the right. And this way we get rid of a lot of the noise in the background signal, and we're really picking up the impact that is only related to the mitigation activities. So you'll see graphs that look like the right, showing the cumulative mitigation over time. So this shows the results of the modeling. It's the cumulative mitigation with the difference between the scenario and the baseline. And we started our mitigation activities in 2017. And so the first thing to notice is there's a wide range of climate change mitigation potential. And it really does depend on the strategy or the combination of strategies that are included. So some strategies we found had a negative mitigation potential. So that would result in an increase in greenhouse gas emissions if they were implemented in some regions. So this graph shows the result of applying the scenario to the whole province, regardless of whether that mitigation would be positive or negative. But that wouldn't really happen. You wouldn't implement a mitigation activity if you knew it was going to increase the greenhouse gas emissions. So we can filter out the regions where the mitigation potential is negative and only consider regions where there's a reduction in greenhouse gas emissions. So this shows the cumulative mitigation in megatons, or millions of tons of carbon dioxide equivalent for the year, and it's the incremental activity that's been applied for the scenarios. And here I've started to play with combinations of scenarios. So it has a forest management scenario as well as a wood use scenario. And you can see there's still a wide range. You can have restricted harvests with more long-lived wood products. You can have harvest less, and these have some mitigation potential. We found that residues for bioenergy has kind of in the middle response. And then we found that some of the higher strategies were really combinations of activities that worked really well in some regions. Now you can say, we know there's not going to be a one-size-fits-all. We know there's going to be different regions that are going to have different strategies that can really optimize the mitigation potential. And so we developed what we call a portfolio of activities. And this selects the best scenario or combination of scenarios for each region and then puts them all together. So we can maximize the mitigation potential for the province. And so that has the highest mitigation potential. And it was about 449 megatons in 2050. That's the cumulative mitigation. Now this includes wood that's cut in BC, and it can be exported and includes substitution in another country. And so we said, okay, well let's limit it to what can be done in BC. And so if we say, okay, we only want to know what BC's mitigation potential is, we still consider the harvest that occurs, but when it's exported, we don't get a credit for using wood instead of steel or concrete in another country. We'll only look at what happens within BC. So this is what the portfolio looks like for BC when we maximize the mitigation potential. So the efficiency of the mitigation options varies by activity and by region. And we are doing analysis at the forest management unit level, and they certainly vary in size and harvest levels. But what we see overall is that the best combination strategy for most places involves higher utilization. So if you're going to cut it, you got to use it. It looks at using the residues that are left behind for bioenergy, for stationary heat and electricity. And it involves shifting the commodity mix away from pulp and paper, a short-lived product, to panels, a longer-lived product. In some regions, the use of bioenergy can't always substitute to high emissions fossil fuel. And so that in the purple region just shows the higher utilization as well as the longer-lived wood products. The other strategy that comes up is the restricted harvest. And we modeled that as not allowing the model to harvest stands that were older than 250 years old. And you tend to see that come out on the coast. Now these results do not yet take into account the environmental sensitivity, the changes in the growth and mortality that Robbie will talk about next. So we are working on including those in the analysis. So I'd like to kind of put these numbers in context by comparing them to BC's greenhouse gas reduction target. So the target is an 80% drop in the greenhouse gas emissions relative to 2007 levels. And so this is, it works out to about a 52 megaton drop that has to be achieved in 2050. So we asked, what contribution can the forest sector mitigation make to this reduction target? And so the portfolio on the far right shows that if we combine activities and choose the best options for each region, we can contribute about 35% of the mitigation reduction target, so about 18 megatons. And as Bernard mentioned earlier, we tried to partition the mitigation potential into where it's occurring. And part of this is so we can assess what the uncertainty and the risks are in each of the activities. So if you look at the portfolio bars, you can see there's quite a large credit in the forest ecosystem. There's a debit in the harvested wood products, and then there's substitution benefits from energy. And so I just want to take a couple minutes and just explain how those bars come about. And I have included all of the scenarios and their combinations on the bottom, but I'll just highlight a couple that are interesting for the portfolio. So one of them is the higher utilization scenario, and it can contribute about 16%. And you find this credit almost entirely in the forest ecosystem. So this strategy didn't change the amount of harvested wood products, so there's no impact on the harvested wood products emissions or displacement. Really what it did was create the same amount of products using some of the residues that would have been left behind as waste and would have decayed or would have been slash pile burned, and we created products out of them. It also increased the salvage harvest, and the end result of that was avoided emissions from harvest as well as an enhanced sink from the forest that was left behind. So that is a forest option. That option really comes out in the forest ecosystem sector and is vulnerable to risks of reversal if some of those trees aren't able to be a sink. We also have included the bioenergy strategy, so the residues for bioenergy. And this one has some interesting positive mitigation and negative mitigation. And really, in this case, we're taking something that would have been emitted in the forest, residues that would have decayed or been slash pile burned, and we're transferring them to a bioenergy facility. So there's a positive in the forest, a corresponding negative in the harvested wood products modeling. And they roughly would cancel out, except we have a big substitution benefit from avoiding the burning of fossil fuels. And to get that substitution benefit, you have to avoid burning the fossil fuels. So that's where the uncertainty would lie for that scenario. And then we have restricted harvest here. Restricted harvest shows a reduction, a mitigation in the forest component as well as harvested wood products. And we found that where this strategy tended to be positive, there just wasn't a lot of young stands available to harvest. And so it turned into a harvest less scenario, quite substantially less in some cases. So there's less harvest, it means there's a credit in the forest, it means there's a credit in the harvested wood products. We did assign a penalty in the displacement, because if you're not using wood, you have to use another product. And so there's a negative product displacement that comes in there. And then the longer lived wood products, you get reduced harvested wood products emissions and a credit for increased substitution. So when you add these components together, you end up with the portfolio mix that describes where the credits and debits will be coming from and what the total mitigation potential could be. Okay, that's the end of part one. I'm going to hand it over to Zach now to do part two.
Good morning, everyone. So following the biophysical GHG or carbon benefit we just discussed, we also look at the cost and or economic impact and the socio-economic impact of the options. So the first thing we look at is the total, the total mitigation cost. So you can see from the graph that for some of those options, like the high utilization, harvest less, and restricted harvest, costs a little bit less. It's about less than 100 million per year. That's the annual average. And some others, like the long-lived wood product, so there's a mistake. There should not no W there. The long-lived wood product and the combinations without bioenergy, a little bit higher, 100 million to 200 million per year. And then all those combinations with bioenergy and the bioenergy options per se has a little bit higher cost. from 200 million to 500 million. And then the portfolio, of course, has the highest cost, up to 610 million per year. So I want to make sure that everybody understands that the mitigation cost here is the change in the total net revenue among the relevant industries in BC. So it's the impact of the implementation of the mitigation options on the industry. So there's nothing related to any investment money or like the amount of cost that any organization or agency should invest. That's just the pure economic estimate of those impact. So, and then we estimate the average cost per ton to combine the cost and the annual mitigation impact into one single index. So if you look at the graph that we map all those options into a graph that's showing those cost per ton values against the annual average domestic mitigation. So the purpose of this graph is show this cost effectiveness of the strategies. So from the higher left to lower right, so we can see the strategies goes more and more cost effective, and the portfolio growth is the most cost benefit options we have, and followed by those different combinations. And those single or individual mitigation options show a little bit lower cost effectiveness. So in addition to those combinations, in addition to those comparisons among different options, we also have the curve called the cost curve to show the variation of the cost effectiveness for each mitigation option over the different spatial units. So that's the example of a cost curve for the portfolio. From the lower left to higher right, we can see there's more mitigation and of course higher cost. So the line is not smooth because each line segment represents the mitigation, the annual mitigation at a certain cost level. So, and you can see that through the portfolio cost curve, we can achieve more than 12 MtCos on average per year at a cost of up to $150 per ton. And 85% of them can be reached under $100 per ton. And then last, we show the cost curve for the same option but with different time period. So that's the example of the portfolio. So that's the, if you want to maximize the domestic or the BC mitigation potential, but in different period, you can see that if you want to do that in 2020, it's gonna give you almost nothing. But if you want to consider the long term, it gives you much more mitigation options or mitigation potential at the same cost level. At last, we estimate the socio-economic impacts by looking at those impact of those strategies or portfolios on employment, on GDP, and government tax revenues. And why we're going to do that? Because that's a necessary complement to assessment of these mitigation costs for policymakers. And how we do it? We just use the multipliers in the input-output model from Statistics Canada to estimate those the socio-economic impact for each portfolio, each option. And the key message from those analysis is that by implementing the portfolio for the longer term, BC can create more than 2,000 new jobs and about 284 million per year for GDP and 34 million per year for the government tax revenue. And that includes all the government levels. Well, of course, that's the average value. So the key message of the presentation, of course, we need to consider a system approach to include the forest ecosystem, harvested wood product, and the substitution effect. And then we need to consider the efficiency of the mitigation options across the region, and carefully ranking the mitigation options over time, because they vary over time. And then forest managers do not control the use of wood, so we need to always combine the forest management with the wood product strategies to make sure we get the best potential. And then we also prove that the portfolios or combination of the strategies can achieve more mitigation at a lower cost level than individual strategies. And options are more cost effective in the long term than in the short term. So the forest sector mitigation could contribute more than 1/3 to BC's target emission reduction target at 2050 at a cost of less than $100 per ton. And by by using the domestic portfolio, we also achieve a lot of socio-economic benefit. And the last one is, of course, the scenarios we are considering right now is a little bit conservative, and we believe that the actual mitigation potential may be substantially higher. And we also be aware of that there's barriers of implementation and costs, and that could lower their mitigation potential in some options. So that's all the results we have so far. Thank you.